Okay, this is lesson 9.6 about absolute value. We all know that absolute value is the distance away from 0. So since it's measuring a distance, the answer always has to be positive. So if I look at number 1 through 6, these are just warm-up easy questions. If I have a negative number in there, the absolute value changes it to positive. So number 1 would be positive 5. Number 2 would just stay positive 7 because absolute values do not just switch the sign. In other words, they don't make a positive negative. They just make sure the answer is always positive. Since 7 is already positive, there's nothing to do here. You can just leave it as a positive 7. Number 3 would change that negative 12 to positive 12. 4 would stay as 3. 5 would stay as 0. 0 is the only number that is not positive nor negative. It's right in between. And then number 6 has a negative number inside the absolute value, so just take off the negative, make it positive 146. For the next ones, we're solving for a variable. You need to think about what number could be in this absolute value to equal 6. This x could equal either 6 or negative 6 because then you're going to take the absolute value of it. Well, the absolute value of 6 equals 6 and the absolute value of negative 6 equals 6. So there are two correct answers for number 7, plus or minus 6. For number 8, it's the same situation. I have y equals plus or minus 3. And for most of these answers, you're going to get two different answers for your variable. G is the same. G is an interesting instance because we have the absolute value of some number equals a negative. Remember that the absolute value was invented to measure distances, which can never be negative. So is there any number that G could be such that I take the absolute value of it and I get a negative 2? There is nothing that G could be, so this is a no solution. The reason being is because I can't take an absolute value of any number and get a negative 2 for an answer. I mean, even if I stuck a negative 2, I have to absolute value that, and that would equal positive 2, not negative 2. So that's a no solution. There's nothing we can do there. On number 10, we're actually going to do some solving. So first, let's simplify these two numbers. I have the absolute value of negative 2, which is positive 2. I have the absolute value of negative 7, which is positive 7. So the absolute value of m then must equal 9. So that means m could be plus or minus 9. For number 11, let's work to get the absolute value by itself, and then we'll solve for x. So first, let's go ahead and subtract this 2, and I get the absolute value of x equals 10. So that means that x must equal plus or minus 10, because the absolute value of positive 10 is 10. The absolute value of negative 10 is still 10. For this one, it's the same situation. Let's minus the 5 across. And then we have the absolute value of x equals 4. So that means that x equals plus or minus 4. For number 13, we need to first add the 4. Remember, we're trying to just to get the b by itself. So I have 3 times the absolute value of b equals 6. Let's divide that 3 away. And then I have the absolute value of b equals 2. So that means that b then could either be plus or minus 2 because the absolute value of either one of those numbers will make that a true statement. Number 14 is the same situation. Let's start by subtracting the 1. And then I have 2 times the absolute value of x equals 14. So divide that 2 away, and we have the absolute value of x equals to 7. So that means that x could either be either positive 7 or negative 7. Number 15, if I subtract the 3 away, I have 5 times the absolute value of a equals 7. Divide by 5, you're going to get a fraction here. That's okay. Fractions are numbers too. We don't discriminate. So we have absolute value of a equals 7/5. So that means that a is either positive or negative 7/5. Just like a whole number. Not a big deal. Number 16. Here's a situation. We have a different thing going on from 16, 17, and 18. We have some number. Let's pretend we don't even know what this is in here. We've got some number in this absolute value that equals 17. So the absolute value of something equals 17. Well, couldn't this whole thing, this something, either be positive 17 or negative 17? because the absolute value of positive 17, of course, gives you 17, but the absolute value of negative 17, of course, gives you positive 17 again, because that's what absolute values do, right? So, since both of these things, since this entire block inside this absolute value can equal either positive or negative 17, I'm just going to take the numbers out of this absolute value, y minus 3, and equal it to either positive 17 or negative 17. Remember, I'm doing this different than the other ones, like 13, 14, those were a lot easier, because if you notice the difference between 13 and 16, these two problems, up above, all of the previous ones only had one variable in these absolute values. Now all of a sudden I've got two things going on within an absolute value. I want to try to get y by itself, but I can't get rid of that negative 3 until I deal with the absolute value. So the entire stuff inside could either equal 17 or negative 17. In other words, I just took the stuff out of the absolute value and set it equal to the positive and negative version of these, of what the original problem was equal to. Now we're going to solve two separate equations and we're going to get two separate answers. For example, on the left side, if I add 3 to both sides, I get y is equal to 20. But over here, if I add 3 to both sides, I get y is equal to negative 14. Now here's the deal, both of these are correct. If I plug this back in, like for example 20 minus 3, that gives me positive 17, absolute value of that of course works out. If I plug in negative 14 and then minus 3, I would get negative 17 in here, absolute value, of course that works out as well. So I have two separate answers here, and again you'll get two separate answers, not plus or minus of the same answer, every time you have more than one number inside your absolute value. So 17 is a similar situation. The stuff inside this absolute value could either equal positive 10 or negative 10, so we'll signify that by setting up two separate equations. Again, the stuff inside the absolute value equals positive 10, or the stuff inside the absolute value equals negative 10, and then we just solve. On the left side, if I subtract 5, I have 3m equals 5, which gives me a fraction of m equals 5/3 for one of my answers. But on the right side, if I subtract 5, because this is negative 10, I have 3m equals negative 15. And if I divide by 3, I have m equals negative 5. So I have two separate answers there. Both of them will plug into this absolute value and end up being positive 10. Last but not least, number 18, we're going to set up two separate equations. The stuff inside the absolute value is equal to positive 3, or the stuff inside the absolute value is equal to negative 3. On the left, I would start by subtracting 2 from both sides. Then I have a over 7 equals 1. Then I want to get rid of this divide by 7, so let's go ahead and do the opposite of divide by 7, which would be multiply by 7. The inverse operation will cancel it out. Now I have a equals 7 for the left-hand side. Then if I do the right-hand side, I'm going to start the same way, subtract that 2 from both sides. But now since that 3 is negative, I get negative 5 when I do that. Still, I'm going to do the inverse operation of divide by 7, which is multiply by 7, and I have a by itself now is equal to negative 35. All right, let's take a look at the back page. We're going to create a table, I'm going to skip the table, honestly. You can create an XY table to graph these, but I noticed that all of these absolute values are in kind of like vertex form, just like we did with the parabolas. And I know that absolute values are in straight lines, so they have constant slopes. Remember that vertex form of a parabola is y equals a times x minus h quantity squared plus k. Well, now we're working with absolute values that are very similar to this. We have still an a, which kind of acts as our slope, and then we have absolute value of x minus h plus k. So these two versions are both like vertex form of either a parabola because we have the squared, or an absolute value because we have this group absolute valued. We still have the same situation going on where we have our vertex kind of showing up right in the formula. It's going to be this number with an opposite sign, comma, this number. So this is the x value of my vertex with the opposite sign. This is my y value. And then what's really nice about absolute values is since they go up in straight lines, we have constant slopes. So rise over run will stay constant. And this number, this a, signifies that rise over run. So if we look at number 19, for example, we want to look at that form and we want to think about, okay, I want to think about this guy in this form, f of x equals some number a in front of the absolute value, x minus some number h, and then plus some number k on the back. It looks like in this case there's no number out front signifying that a, so I can think of this as like a 1 because 1 times x would not change this equation. And then similarly, there's no h in here. So we can think of what's going on inside there as there's x plus 0. In other words, my h is 0 because there isn't one that exists. And then I see my k is 3. All right, well then vertex form tells me that it's h comma k, or my vertex is going to be this 0 comma 3. And we of course don't have to change the value or the sign on 0 because it doesn't have a sign to begin with. So I can start my vertex from the origin, and then I have to go up 3, so my vertex is going to be right here. Next, from there, I'm going to grow from a slope of up 1 over 1. Again, my slope is like this a. Since it's a 1, if you turn that into a fraction, it's 1 over 1. So I have rise over run. I need to go up 1 and then positive or right 1. So if I did that, I would be growing in this sort of fashion, and you can start to see half of your absolute value graph growing. Axis of symmetry would be right down the middle of that vertex. So then the other half would also be going up 1 over 1, but just kind of like off to the left. It's going up 1, left 1. And then you can see that this forms a perfect symmetric V, and you've got your graph for number 19. Number 20. If I look for my a, the number out front, there again is not an a, so we'll say that my a is 1, or my slope is going to be 1 over 1. I have an h value, but I do not have a k value, so I'm going to say my k is 0. So that means my vertex is not negative 3, but positive 3, because we always switch the sign on the h, and then comma 0 for that k value. So that means my vertex is going to be right here, and then I have an up 1 over 1 slope. So again, constant, just rise over run. And then of course it has to be symmetric, so I have the other side of that growing as well. Number 21. Number 21 is going to work the same way. It's missing a lot of pieces. Let's again think about y equals a times x minus h in absolute value plus k. Here I can see that my a is negative 2, or my slope is going to be negative 2 over 1 if that was a fraction. So that means that I'm going to rise negative 2. So that means I'm going to go down 2 and then positive 1 when I graph this slope. My h looks like there's a 0, and my k looks like there's a 0. So that means I must be starting at the origin. From here, I'm going to go down to positive 1, down to positive 1, down to positive 1. And you can start to see my absolute value graph growing. If I use symmetry to get the other side down to, I would be going left 1 this time. And then here's the other half of that V. Before you jump into number 22, you might want to pay close attention to the fact that we have an inequality going on. It's not a big deal. It's not going to change the graph that much, but there will be shading. And in this case, we need to have a dotted line for our absolute value because there's no equal to sign underneath. Okay, so be careful here before you connect your dots. Make sure you check to see if it's equal to, less than, greater than, whatever. All right, it looks like here that we have a absolute value V that has an x value vertex of negative 1, right? Because I'm looking for my vertex here, so it's going to be negative 1, comma, and then there's a plus 0 on the back, so 0. Again, I stole those numbers from my h, switch the sign, and my k, leave the sign. So that means my graph is going to start right here, And then I'm going to grow with a slope of 3 over 1. So I'll go up 3 over 1. And then I could do it in the other direction for the left-hand side as well. Now be careful, don't connect these dots quite yet, because we have to remember that it is an inequality, so we are going to connect these dots using dotted lines. Again, that's because this is not equal to, it's not less than or equal to, it's just less than. And now we need a shade. H is less than that value, so that means that we're going to be all underneath, so that's down here. So this graph is all these values under here would make this a true statement. Number 23 is not an inequality, so it's just a straight line, no shading, we'll be good to go. It looks like here that my vertex is going to come from here, so positive 2, comma 4. Remember, we always switch the sign, leave the sign. Positive 2 up 4 is right there. Looks like our slope out in front is positive 1 over 1 because there isn't really an A there. So then it just goes up 1 over 1 to the right, and of course up 1 over 1 to the left for that absolute value graph. Perfect. Number 24 is our last one, and if you notice, it's an inequality, so we're going to have to graph this one with a solid line in this case, and then we're going to do some shading. It looks like my vertex is going to be at negative 3 comma negative 4. Again, switch the sign, leave the sign. So if I go left 3 and then down 4, I have a vertex right here. Looks like my slope is going to be up 2 over 1. So I'll go up 2 over 1 and put some dots. I'll do that a couple times until I get the general form of what the graph is going to look like. And then I'll do that as well in the other direction so I have a symmetric graph. All right, I'm ready to fill this in, and I notice that this is a greater than or equal to sign, so I can go ahead and use a solid line to connect these dots. Next, since this is greater than, I need to shade on top of. So in that case, it's going to be inside this graph, all the place inside. Okay, there you have it, some nice graphs of absolute values. Remember just to use the same tricks and shortcuts we use from parabolas, graphing with vertex forms. It's pretty easy. We don't even have to plug in points on this one. So these are my favorite things to graph. Easy, easy, easy.